Communications Document Management Project. I am the team lead, Jacob Duar. This is Matt Musette, Kyle Page, and Anthony Sayati. Kyle's another group member. He was a grad student who helped out for a few hours here and there, helped with the API and web scraper / database. So the main objective for the whole project was that there was a very good need in the weather industry for gathering all the data, because these weather reports come in from so many different outlets, whether it's social media, radio, weather spotters out in the field. And what our job was to kind of gather all that information together, upload that to a database, and also create a portable system. And by portable meaning someone can take this apart and break it down into a large either case or bag, and then go back, throw it in their car, and go back. And the impact from this would be to then change how weather is gathered by Skywarn. A portable weather station can be placed in the field and take its place of spotters. So a spotter is just someone who records data. Right now, many of the spotters, like for rain and snow, they do that stuff manually. So to read rain, you have to go out to the RAS, read that rain gauge, and then go and send that back to the computer and go on. So right now, we want to be doing that wireless. So the project overview, in that photo over there, that is our sponsor and his crew on amateur radio club. So they sit there throughout the storms, gathering all that data coming in, and they then search through that, whether it's whether that data is actually correct, basing it off multiple reports that are coming in, and then they then have a system. So right now we needed a system to electronically upload that. So kind of like bypassing the whole gathering of that information. Our system would measure electronically, send to a receiver, upload that to a text file, which is then uploaded to the weather vault database. And right now I'll bring that over to Matt.
So this project was a continuation of last year's group. Last year's group had temperature, humidity, a wind sensor, pressure, and they also had a camera on theirs, and it would take all this data and store it locally on an SD card. We ended up taking the camera and SD card out, and we didn't have much time to incorporate that back in. So this is the before and after pictures. The one on the left is the original project, and then I wanted to clean that up because I couldn't really troubleshoot that and add wires in it to it. And the board, you can't really, board's here up underneath. They used hot glue to put wires on, and so it was covering pins, and I couldn't put new wires in there. So I added batteries, I added a switch. There's this potentiometer that controls the LCD screen, which isn't here, but this is one of the connectors, and it just sits right on top of the microcontroller. And then I added terminal blocks, just to make it easier to unplug power and ground and have everything go to one central point. And then we hit a junction box. I call it a junction box. It's right here on the stand. You can see that. It's got most of our sensors. It's got barometric pressure here, temperature here. The camera can go here, and the SD card right here. And then right here is the Ethernet breakout for our wind gauge up there. And again, same principle. I just wanted to break that up, make it, redo it, make it easier to get into, and add more wires to it. This is our system diagram, just a basically overview of what we have going on here. At the center, it's kind of hard to see, that microcontroller, the Atmega 2560. And then I just put these walls in here as, just to say that this is outside of the microcontroller. You have your thermometer, then your pressure, wind, camera, and wind's over here. And then our new things we're adding is the snow measurement. It's a light. We'll explain later that it's an infrared sensor. And then our rain here, which is all going to be transferred, exported to the weather vault database for use by the weather spotters. Our customer requirements, all we had to do was create a snow gauge that was accurate to 1/4 of an inch. It was originally 1/10 of an inch, but our sensor couldn't get that accurate, so we bumped it up to 1/4 of an inch. And then our rain had to be accurate to 1/100th of an inch, which seemed impossible at first, but after some testing, it actually worked very well. And our API, which is what we're sending all this data to, it's going to scrape all the data from the different websites and bring it together so you can look and see where that type of weather is at which station. Stability, we had a requirement to have it stand, the stand had to stand in 100-mile-an-hour gusts and then 80-mile-an-hour winds, which is a lot. We couldn't really test that because there isn't a wind tunnel and the mathematical calculations is a little difficult. So we just added stakes at the bottom here that we're going to stake in the ground, or the last year's group had rings that sat around here and had rope that came down to more stakes, so it's added stability to it. And then our customer wanted a manual so that you can look at it, be able to easily break this down and take it anywhere. And these are engineering requirements. It's pretty much the same as our customer, accurate to 1/4 of an inch, accurate to 1/100th of an inch, and then the API has to be able to take this data, scrape it, and put it together. We had a lot of constraints with this, such as time, which I think everyone did. We could have added that camera and SD card if we had a little more time. And then the big one was the memory of the 2560. We were originally going to have 3 sensors because we decided, if there's snow drifts, then you're going to have inaccurate readings. So we decided to take 3 and average it, and that would be our reading. But because of the memory, we had to stick with 1. So we got the idea out there, and we were able to do that. And then the measurement of the wind, if it's any less than that, it's not considered worth reporting. So we had to make sure that it could withstand more of those winds. I'll pass it back over to Jacob.
So moving along throughout our semester, this is focusing on our snow gauge and rain gauge. Obviously with the snow, Mother Nature was pretty much how I was dealt to kind of test. So as you guys all know, this past winter, we didn't get snow or significant snow totals till March. And that was and that was pretty tough just because the testing would be like, all right, 1 week, all right, snow gauge doesn't work. If we're going to try and scramble something back together for the next storm that's coming next week, try and come up with a solution is kind of tough on that week time frame. But even going back to even earlier, our snow gauge was accurate to that original 1/10 of an inch. But because of that, it was due to just because we didn't have such significant snow totals. As that snow totals got higher and higher towards the sensor, we noticed that it got very more inaccurate. And that was just how the sensor outputted its data. And then just moving along, just testing. Testing kept getting pushed back, whether it was waiting for different parts to come in. And if we could have just done that a few weeks earlier, we would have much more time. And then, again, just moving forward, you can see that all of our planned hours, we were kind of on schedule at some points, but then most of the testing and actually integration and of the XP for transmitting and stuff like that, which is a final component to add in, that kind of got delayed just because of the testing that we couldn't do earlier. So for the verification cross-reference matrix, you can see that most of it was just testing for us. We had to, with the snow gauge, we had to we had to test it. Could it get accurate to that 1/4 of an inch? Could we transmit every 10 minutes? And are we transmitting to the weather vault database? And that was going through also to the rain gauge. Is it accurate to the 100th of an inch? Can we transmit to the weather vault? Can we transmit every 10 minutes? And through testing, we proved that we could do that. And then with the API, the web scraper, could we scrape that data, get it all together, and then send it off to the weather vault database? And then stability, that was the tough part. We couldn't really test it, obviously, because we don't really have 180 or sustained winds up to 80 miles an hour or 100 mile an hour sustained or a gust. So testing in that was kind of tough. we decided we were going to try and analyze or kind of do tests and mathematically calculate it, but with time we couldn't really do that. So starting at the beginning of the semester, we had a couple alternatives that we could have done. One of the simpler one was just using a camera and ruler. So we would have a physical rule that was always could be mounted there. Then we'd have a camera fixated on that, and then using a software, we could convert that into inches. We didn't really look into any like camera software to actually do that. So we kind of looked into the method 2, which kind of would take in the rain gauge, which it would be the load cell. And the load cell, it has 3 wires, or 4 wires. Those 4 wires are then caught to the load cell. And then as weight sits on that, it bends that aluminum bar, and then that sends a voltage back through the wire, and then we would convert that to a set amount of inches. But with snow, it's not that easy because temperature, dew point, that all plays into the that all plays into like the weight of the snow, and then converting that into inches would be very tough. So we ended up moving on to the sharp infrared sensor. The sharp infrared sensor on turn on for the setup, it would take this initial reading. It would take it off that white snowboard. It would take that initial reading, whatever the set height is. It would store that. Then as snow accumulates, it then takes those readings off of the snow and then reports it back to the LCD, which is also then printed into a text file and getting sent to the weather vault database. One of the requirements was that it was just transmitting every 10 minutes. So everything on here was already transmitting 10 minutes, so that was easily integrated into the system. Moving along for the snow gauge, later testing, which was involved just at my house, just piling up the snow into a big, like 36-inch cube, and then cutting 2 inches off every single time, we created these data points. When we inputted this data for the sharp infrared sensor to calculate a set amount of inches, we saw that it was very inaccurate because that best line fit didn't always correctly calculate that set amount of inches when it was either 8 inches or when it was at, say, 32, 36 inches. So we decided to make a piecewise function breaking up that line so we can get a little more accurate data. That proved to be a lot more effective, and we then got that back down to the 1/4 of an inch accuracy. So this is just some snow gauge testing. We weren't able to gather many snow gauge testings with the actual field testing with snow. So this is just a lab test. And in the left picture right here, we have this would be calculated as 36 inches, but we are saying that the set inches, if I threw a calculation, would be 0. We raise that up to 2 inches, and you can see on the right, this is the text file that is printing from this main weather station with the humidity and everything else. We see that the first reading gets taken at 0 inches, and then after running through that again, we get that accurate actually to 1.01 inches. So the reason for that was that the snowboard doesn't have the type of reflectivity as snow does, just through like the crystals and stuff like that. And we saw that light affects the snow very much. So when it's midday or dawn or at night, those numbers changed. So we actually had to create theoretical values based off of our last 2 graphs to then create theoretical lines that would work for different times of the day. And then we ended up inserting that into the code. Obviously, with no more snow, we can't really test those theoretical lines, and we'd have to wait until Rob could test that next year. And moving on to the rain gauge, I'll hand it over to Anthony Sarah.
So with the rain gauge alternatives, there was 2 actual ideas we had off the start. Because of the constraint of the Cocoa RAS, it was a little hard to develop ways to incorporate that with the rain gauge, making it digital. So originally we thought of a flow meter, and the flow meter, you'd have to pour the Cocoa RAS into it, so it would get the voltage output through it's like a fan, like propeller inside. But the issue with that is we'd have no way to pour it, or we'd have to develop a way to pour it, which would be very hard. And we also would only be able to get one measurement rather than transmitting constantly. So we decided to go with a load cell to actually weigh the cocoa rasp with the rain inside. So it basically eliminates the weight of the cocoa rasp and puts the weight of just the rain, and it gets it in grams, and then we converted it to inches. So then that ended up working out a lot better than we thought it would, and that's the way we went. So the actual design, as you can, I think most of you can see. So we got the AT Mega 2560 right inside this box with the XP, which is right here, and then we have the amplifier for the load cell, and then there's a weatherproof wire right here that is attached to the load cell, which is underneath the cocoa rasp right here. And then we 3D printed this top part that holds the cocoa rasp very firmly. And then it's easily detachable too, so you can take it apart and bring it along. So with that, so yeah, there's 2 batteries, so you just switch it on like this, and then it's ready to start taking readings, and it transmits to the receiver. And I have a quick demonstration that will show that. So right here, just showing that it's empty. It's reading 0 inches. Then I think it's 0.3. And then right here, it's at 0.49. It shows the next reading. I'm gonna give it to Kyle.
All right, for the next few minutes, I'm going to run through all of the design philosophy behind the additions and improvements that I tried to make to the tripod. The first is the gauge mounting system. We had a challenge presented to us of actually finding a way to mount the cocoa rasp gauge and the load cell in order to take the measurements for the rain in such a way that was both cost-effective as well as easy to mount and dismount for storage and portability. So for this part here, we have 2 components, and I'll go through the actual full assembly once I've gotten through the individual parts. But the first shown here is the bushing, which sits in the top of the tripod. So beyond that, we also have an L bracket, which serves to space out the load cell above this. That way it's not only cantilevered so that I can accurately take measurements, but also will center the cocoa rasp and load directly above the tripod so as not to create any kind of moment that would cause the tripod to tip over. So this is essentially a part made of 6061 T6 aluminum, and the reason for this was corrosion resistance due to the fact that this is going to sit outside for most of its life. So we need something that is not going to rust or corrode that would cause any difficulty in removing it from the actual tripod. As well as this durability, this is something that needs to be lugged out into a field, potentially assembled, taken back down, and brought home. So if this is ever bumped, falls over due to the wind, etc., we need this to last. Beyond that, it was also lighter weight than other materials, which again lends itself to portability. So instead of using a steel part, we saved a little bit of weight with using aluminum. Next is the L-bracket that I mentioned earlier. Same idea as far as material choice, and we've already went over the actual design philosophy for this. The other thing that I tried to take into account in both of these designs is ease of manufacturability. So I wanted to create parts that would require as few machining operations as possible. That way this would be easily reproducible. Finally, we have the entire assembly. You can see on the bottom here, we have the actual bushing. Above that, there's the L bracket, which mounts into the actual load cell. In the middle here, we have the pin, which is centered top to bottom in this part in order to secure this to the tripod. Beyond this, we also have a couple of other pieces of hardware. We have a pair of 1032 screws as well as a pair of M5 screws that interface directly with the web zone. Next, we have the actual tripod leg end parts. This was an effort primarily born out of the fact that the tripod design previously was not stable enough. We found that the nylon cords and stakes, which were tied to eye bolts driven through the legs, allowed the actual tripod to deflect in the wind and potentially fall over. So the idea behind this was to try and provide a rigid mounting point where there was no deflection for that tripod to gain any momentum and fall over. So this is a simple, again, 6061 T6 aluminum insert, a simple turn part which can be done in 1 or 2 machine operations. It has a threaded hole down the center which accepts a stainless steel 3/16 eye bolt, again, corrosion resistance being a primary driving factor for material choice, especially seeing as this part will be in direct contact with the ground. So if there is moisture, it's going to be directly exposed to it. Next, we have the actual completed design for this part. As you can see in the diagram here, it demonstrates how the parts interface together. This part then, in turn, was epoxied and placed inside the bottom of the leg for durability and strength.
And then to move on to the API, we're just going to go through a little demo of how we're actually getting the data getting web scraped and then uploaded to the database, and then also for our systems that are printing to a text file, how we're actually uploading those text files to the database as well. So as most of the variables that he is typing in, those are all given to us by the MesoWest API. Those are all on their website. Those are all inputs that they are acceptable inputs. And here he's saying the past 24-hour precipitation accumulation, the comparison is he wants to see everything that is less than 2 hours, and for the air temperature, he doesn't filter that. He wants to see all the weather stations that are transmitting the air temperature, wind gusts of less than 30 miles an or wind gusts less than 30 miles an hour, and wind speeds greater than or equal to 20 miles an hour. And then this is just going to go on to then, after he submits it, that's just going to pop up with how many weather stations with that given data were actually scraped. As you see in that top corner, there were 43,000 stations with all of those filters that had data that we wanted to look at. And then next, he's going through the text file. So this is the text file that we are printing all of our weather data to, and these are the new entries that were in that text file that is then going to get uploaded to the database. And after that, we're just going to open it up to questions.